In this video, I'll do a quick example of finding the sum of a geometric series by using the formula we just proved a moment ago. So let's start with a simple example like the one I was mentioning. Let's say we have 2 plus 4 plus 8 plus 16 and so on. You know, we have this geometric series. And sort of like the practice questions we did back in chapter 1, uh, let's just say it ends at some really, really large number, whatever. Let's just say 256 for the sake of argument. So, and the point, like the question is, what is going to be the sum of the series? What does this all add up to be? So if I'm going to utilize this formula, I need to know all of the components of it. Is like, what is A, what is R, what is N? And remember that A was the first term, just from review. R was the ratio, and N, capital N, is the last term of not the term itself, but the last term index. So if I'm trying to deal with that very specific series, if I know that it's geometric, which it is because I just invented it, but notice that I know A is the first term, R is the ratio, which is 2. It's multiplying by 2. So basically, I've gotten A is 2, R is equal to 2 because it is being multiplied by 2 as it goes. And so the only last thing that I need to know is, well, how many terms is in this series? Because I see 5, but obviously there's going to be an unknown number of terms going on in the ellipsis. So there's various ways that I could figure this out. You could do it by brute force, just by simply multiplying by 2 and 2 and 2 over and over and over again. But one thing I could do is by recognizing the formula of this series, which is AR to the n minus 1, and then trying to figure out n by setting that equal to its final value. So let me do this all in green, just as one potential way you could do this. So the series is 2 times r to the n minus 1. So this would be our generic formula for a sub n. And my question is, well, what is the index n on that? And that's really the only unknown that I have in there. But what I do know is that that formula equates to be 256. So I know the value of the nth term, I just don't know n. So I could figure out what index it would be by solving this equation. So if I divide both sides by 2, that would give me 128 is equal to 2 to the n minus 1. I could then take log base 2 of both sides, because that would cancel base 2, as we know for solving exponential equations. Log base 2 of 128 should be what exponent I need to take to get to 128, which I believe is 7 if I had to guess. But let's go ahead and use our change of base formula, log of 128 divided by log of 2. Oops, I definitely need to close my parentheses there. That will be very wrong. Okay, which is 7. Okay, my guess was correct. 7 is equal to n minus 1. And then I could add 1 to both sides, which would give me n is equal to 8. So moving back to the question, I've now figured out how many terms are in this series. 8 terms. And I could kind of make sure if that makes sense. By just doing the math. 2 times 2, 4, 8. So this is one way I like to do it is, you know, if I'm trying to do it in my head, I count with my fingers. 2, 4, 8, 16, 32, 64, 128, 256. That is 8. Perfect. Anyways, that is n. Cool. Now we have everything we know to figure out the nth partial sum. So basically, if I want to know S8, which is just the sum of the first 8 terms of that series, which is just, again, exactly what I have written right there, all of that. The whole point of all this is that this formula gives me the solution without having to do a whole bunch of math and will give me that sum. And basically what you do is it's going to be a, which is the first term, times 1 minus r to the n, which is 2 to the 8th power, because that's the end index. And it's going to be all divided by 1 minus r, 1 minus the ratio, which is also 2. And so what that will end up giving me is 2 times 1 minus 256 divided by negative 1. And it's very strange, and it's like, well, why does this all add up to that? But that was exactly the point of the last video, is that was a generic proof of this fact. So it's not a coincidence, just it's algebra. But what that leaves us with is 2 times negative 255 over negative 1. So of course that ends up being positive because it's a negative over negative, and 2 times 255 is 510. And that should be the sum of all of those numbers we have there. And we could check via attrition. So this is a step that's totally not necessary, because it's that this formula that we proved is always true assuming we're dealing with a geometric series. But let's just go ahead and do it manually. 2 plus 4 plus 8, add up the terms of this geometric series. And at this point, you're like, well, we could have added it up manually by hand a million times over. But the point of this demonstration is to recognize the importance of that formula, where this could work for 100 terms or 1,000 terms, and think of the amount of calculation we're saving instead of having to do a bunch of adding. And there's actually a kind of a neat geometric way of thinking about this proof too, which I don't want to get into. But there's other ways to make sense of this that are a little bit easier. And let's go ahead and wrap this video up and move back into annuities in the next one.